students, welcome to today's YouTube lecture. Myself Dr. Sohail. I am a PhD in chemical engineering from the University of Technology, Roorkee. So in my previous video lecture, I have actually shown you, we have discussed regarding the heat transfer through a composite wall. I'll be providing the link in the description box. So today I am just showing actually a numerical example regarding that. So here you can see we have a solid composite wall made up of three different layers. One is a brick layer, then is the middle cement layer, cork layer, then is the inner cement layer. So these three different materials, they have different thickness here and different thermal conductivities, and we have the outer surface temperature is given. T1 is 30 degrees Celsius and it's 15 degrees Celsius. So first we need to, we will consider the unit area of the wall. We will consider unit area of wall. That's we consider A is equal to 1 meter square. So first, if we calculate the thermal resistance of the brick layer, R1, I call it R1 brick. That's for the brick layer. So it will be L1 by K1A. So L1 be equal to 0.25 meter divided by K1 is 0.7. Its A is area. It is coming out to be 0.357 degrees Celsius by watt. And similarly, this is R2, the thermal resistance by the cork layer. R1, R2 cork. It will be L2 by K2A. So it should be equal to 0.10 divided by its thermal conductivity is 0.043 multiplied by this 1, it will be equal to 2.326 degrees Celsius by watt. And similarly, if you find the R3 for this cement here, it will be equal to L3 by K3A. It should be equal to 0.06 divided by its thermal conductivity is 0.72 into this, so it should be equal to 0.083 degrees Celsius by watt. Now we need to find the total thermal resistance of this composite wall. It will be equal to the addition of these three, so that will be R1 plus R2 plus R3. So when you add up these, so you should come 2.766 degrees Celsius by watt. So this is actually the total thermal resistance by the wall. So now once you have found this total thermal resistance, so after this you have to find out the temperature driving force, because then only we can actually find the rate of heat transfer. So now we will see what is the temperature difference. This temperature is 30 degrees Celsius minus, and inner temperature is 15 degrees Celsius, so it will be equal to 45 degrees Celsius. Now rate of heat transfer by the wall, rate of heat transfer by the wall, you know it should be equal to, Q should be equal to temperature driving force, that's 45 degrees Celsius, divided by the total thermal resistance, that's 2.766 degrees Celsius by watt. So when you calculate it, it will come out to be 16.27 watts. That means Q, the total heat transfer by the wall, is 16.27 watts. Now we have to calculate the interface temperatures between these layers, brick layer and cork layer, and then cork layer and cement layer. So now T1 minus T dash, we can write Q1 L1 by K1A, or it can be Q1 into R1. Sorry, this will be Q, because the Q will be same throughout this layer. So T1 is, what is T1? T1 is 30 degree Celsius minus T dash, it is Q is 16.27 multiplied by this is R1 0.357. So if you calculate it, T dash should be equal to 24.2 degree Celsius. That is the interface temperature. This T dash is the interface temperature between brick and cork layer. These two layers, this is the interface temperature. Now after this, we have to find out the interface temperature between the cork and the cement layer. Now after this, we have to find out the interface temperature between the cork and the cement layer, that is T dash minus T double dash. It should be equal to Q L2 by K2A, or it is same as Q into R2. So T dash already found, we have is 224.2 minus T double dash, it in 16.27 Q into L2 by R. This R2 is 2.326. So from this, if you find is T dash should be equal to 24.2 minus this will be equal to 37.8. So it will be equal to minus 13.6 degrees Celsius. So T double dash is minus 13.6 degrees Celsius. That is the interface temperature between cork and cement layer. These two layers, the interface temperature is this. Now after this, we need to find the percentage of the thermal resistance. What is the percentage of the thermal resistance offered by the different layers? The percentage of thermal resistance offered by, let's suppose first, that is brick layer. How much thermal resistance percentage is offered by the brick layer? So that will be equal to the thermal resistance of this layer. What is the thermal resistance? Is 0.357 divided by the total thermal resistance, that is 2.766 multiplied by 100. So this will give you the thermal resistance offered by the in percentage terms. So it will be equal to 12.9%. So this will be the percentage of thermal resistance offered. Similarly, for cork layer, percentage thermal resistance will be equal to its thermal resistance, that is 2.326 divided by 2.766 multiplied by 100. It will be equal to 84.1%. That means the maximum thermal resistance is offered by the cork layer. Similarly, for cement layer, that is the inner cement layer, what is the percentage thermal resistance? So that will thermal resistance of this layer, that is 0.083 divided by 2.766 multiplied by 100. So it will come out to be 3%. So 3% should be the thermal resistance offered by this cork layer. So now after this, if you have the heat transfer by this is only 70% of what the heat transfer is. So if the desired rate of heat flow through this wall, if we want the rate of heat flow through wall only 30% less than the present value. So what would be the thickness of this? So what will be the thickness of the cork layer? So that if we want 30%, so that means heat transfer Q should be equal to 0.7, 70% of what is presently, that is 16.27. So this heat transfer will come out to be 11.39 watts. So this must be the heat transfer if we want 30% less. So in this case, what will be the required thermal resistance? It will be equal to temperature driving force, that's 45 degrees Celsius divided by 11.39. So it should be equal to, if you divide it by this, so it should be equal to 3.95 degrees Celsius. So this much should be the thermal resistance. So when you have actually this thermal resistance, so that means the additional thermal resistance that will be needed, that will be equal to 3.95, and what we have already is 2.766. So that means the additional thermal resistance will be 1.184 degrees Celsius by watt. So if you want the desired heat transfer rate 30% less than the present value, so this much thermal resistance you have to add to this wall. So that means the thickness of the wall, what additional thickness then you have to provide to the wall then. So now additional thickness of the wall needed, what will be the additional thickness needed, that will be equal to, now we know R will be equal to L by Ka. So now R is basically 1.184, that's the thermal resistance. L will be thickness, additional thickness. So K, so since we are considering for the case of cork, so what additional thickness of the cork is needed, so it will be 0.043, because the thermal resistance of the cork is 0.043 and multiplied by area we are considering 1 unit area. So this will actually give L is equal to 1.184 multiplied by 0.043. It is coming out to be equal to, multiplied by 1 also, it will be 5.1 centimeter. So basically this additional thickness of the cork has to be introduced. The thickness of the cork has to be additional this, that is 10 centimeters, so you have to add 5.1 centimeter more, so that the desired rate of heat flow through this wall is 30% less than the present value. So I hope you have taken this problem well. So in my next videos also I will be trying to showing some more numericals and trying to further elaborate the concepts, so you can try out more problems at your own places. So please like, share and subscribe to my YouTube channel, and also press the bell icon for any future notifications, and please stay safe, stay home. Good luck. Thank you.